This is the Rising Phoenix Dev, and today we're going to actually write a quantum program in Visual Studio with Q#. Now, I'm going to have this tutorial on my other screen so that way I can view Visual Studio and you guys can see what I'm doing. I will explain everything that's going on as according to the tutorial on everything that they say, so you don't have to worry about that. So just scrolling through, and we're pretty much going to go all the way up to step 5, creating superposition. Everything else from there on out, you can view the tutorial. I'll have a link in the description, so you can follow along from there, and also do other tutorials that Microsoft has. So let's get started, shall we? Alright, so now let's actually go ahead and build the bell test project. So first things first, let's define what we see here. We see a namespace, quantum bell test. Namespace works as it does with any other programming language that utilizes those, and it's a means of organizing. Now, I should state that Q# is not an object-oriented language. It's more of a procedural language. Keep that in mind. The open keyword is the same as it is in F#, which is basically a using statement. So we're using the Microsoft Quantum Primitive and Microsoft Quantum Canon namespaces. Operation, you can think of it as a function or a method. And of course, the other operation here with the capital O, so you can see that they are not case sensitive, is the name of the operation, function, method, however you want to call it. Here is our arguments. Now, the arguments take a tuple value, which means we could have a string and an int, and a few others that actually occur only in Q#. Colon here designates that, sorry, and these brackets are your return type. So the colon here points to your return type and specifies what it is. And again, the return type is a tuple, and an empty tuple represents what would be in F# unit, or in C# void. We have here the body, which is where our method statements go, or our definitions of the operation go. So let's get started. Now that the basics are out of the way, let current equal mq1. And I forgot. I need to set the arguments. And the arguments are desired result, which is a string value, q1, qubit. And qubit is, well, the easiest way to describe a qubit is a state, which is in quantum physics. Obviously, because this is a quantum programming language. Alright, so if desired is not equal to current x q1. Now, x is a gate switch, which means if q1, let's say for example, q1 is 0, but we don't want it, we don't desire it to be 0, we want it to be 1. Then this gate switch will actually flip it over to be 1. Okay? We also want to change the name from operation to set. That's the name of the function we want it to have. So next, let's define another operation. spell test. Spell testing. Count. Int. And int within Q# is int64. And initial result, again string, and we want the return type to be a tuple value of int. Body mutable num1s equals 0. Now, in Q#, it's basically the same as with F#, which every value type is immutable unless you specify otherwise. And I believe with C# they're kind of doing the same thing. With C#7 that is. And we will be using quite a few C# features in this. Just to be aware. So next, we want a using statement. Qbit equals qbit1. So here we are specifying that we want our qubit to be 1. For test in 1.count. So here's the other change when it comes to Q#. If you're unfamiliar with Python, this is what a for loop looks like in Python. And I hate it. Set initial qubits 0. Let res equal m qubits 0. So, the let keyword, again, appears in F# and pretty much every other functional language out there. It's basically how you define a variable. And in F# it's actually a lot more than just that. It allows you to create functions using it. But enough about F#, let's continue on. The M is another switch, but I will talk more about that in a moment and further specify on the X gate as well. So if res equals string value 1, set num1s equal to num1s plus 1. Set 0 qubits for a 0. Bam. And then finally, return count minus num1s num1s. And I really hate that my keyboard likes to do that. So, as you can see, Q# does use the brackets just like C# does. It does require the semicolons just like C#. So just to be aware that we are mixing like 3 or 4 different programming languages into one with this. We have F#, C#, C++, HTML, and Python so far. So, let's move over to the driver. The driver is a C# class, and it's what allows us to do our test. So, we have our using statements of Microsoft Quantum Simulation Core and Microsoft Quantum Simulation Simulators. Those are important, especially with Quantum, because this is what allows us to do our testing with Quantum on a classical computer. In the main method, using var sim equals new quantum simulator, result initials equals new result. You bitch. Result dot 0 result dot 1. For each result initials var res equals bell testing dot run sim 1000 initial dot result var num zeros num ones equals res. And then the full qualified name of system.console.writeLine. And C#7 feature here. Init initial -4 every fucking time. Zeros equals num zeros -4 ones equals num ones -4. There. And now drop down to, and then fully qualified name, system.console.writeLine. Press any key to continue, ... and fully qualified system.console.read key. And let's run this. There were build errors. Why? Return statement and a statement. Return statement and a statement. Let's see here. That would be why. Oops. We want it to be outside of the using statement. It's compiling. And as we can see, init 0 zeros 1000 ones 0. Init 1 zeros 0 ones 1000. Press any key to continue. And sadly, this was only utilizing classical programming techniques. So, well, I shouldn't say classical programming techniques. This was just a classical example. So before we continue, let me talk about the X and M gates. Okay, so the M gate, let's start with that one. The M operation measures its argument qubit in the computational Z basis. The X operation applies a state flip around the X-axis to its argument qubit. Now that we have talked about that, let's create a superposition. So that way we actually have a little bit of quantum mechanics thrown in. So on the Q#, let me see here. in bell testing, we want to perform an X gate before we measure it in bell test. So X qubits 0. Then let RES M qubits 0. So let's run it again and let's see the results. 0. Again, pretty much the same results. So now there's another gate, which is an H gate, or I hope I pronounced this correctly. A Hadamard gate. So we'll change that X gate to an H gate. Let's see what happens. We get init 0, zeros equals 474, ones equals 526, init 1, zeros equals 509, ones equal 491. So every time we measure, we ask for a classical value, but the qubit is halfway between 0 and 1, so we get statistically 0 half the time and 1 half the time. This is known as a superposition and gives our first real view in the quantum state. Now we could go a little bit further and do quantum entanglement, but I think you guys can actually pull up the tutorial yourselves and write the code. So minus that one minor setback of oops. It's pretty straightforward and not too difficult to work with Q#. So before we go, we're gonna do one little thing. We're gonna do an X qubit 0 before we run the H. What happens then? 482, 505. Let's do it again. And let's have a little bit more fun. We're going to run an X, an H, and an X again. 508, 497. That's actually more statistically 1-to-1. But it looks like the X gates don't actually do anything when you actually run the H gate. That's a shame. Alright, this has been the Rising Phoenix Dev, and I'm signing out. One more thing before I go. Whenever you're learning a brand new programming language, it's always a good idea to play around. Whatever you learn, just play around with it. It's like we could remove the mutable from num1s and see what happens. So run it, and there were build errors. Why? Because num1s is undefined because it's immutable. So it's always nice to see exactly what happens whenever you just run a stupid little test, like what happens if we put qubits to be 2. And then we run it. So I always recommend to just do a stupid little test with everything that you've learned with the new programming language. It will allow you to learn more in the long run. It's like, well, we know that results is there, but what about string? Is string there? Why, yes it is. Is big int there? Good question. Let's see what happens. Build error. Unknown type. Big int. What about float? Badly formatted or unrecognized. Okay, so what happens if we change the int to be float? Badly formatted or unrecognized. So let's actually do the proper naming convention of float. Operands have different types, float and int. So float. What happens when we do that? How about float, float? So we can see that doing little tests can definitely give us interesting results, or if any results at all. Alright, you guys have a great one. I'm signing out and I'm going the hell to bed. I gotta work in the morning.